Time to do some practice with antiderivatives. In this case, we know what the outcome of the derivative is. What we're looking for is what did we put in and what function led us to a particular derivative. Now, it seems sort of a novel thing to do, not so clear yet what some of the applications are, but it'll turn out it's really interesting. Lots of amazing things you can do. So it's important to really get good at taking antiderivatives, but also be careful about what you can and especially cannot do. So you want to do practice. You really want to make sure you say, I know I can do this with confidence, and I know I don't want to do that because that won't give me the right answer. So practice, practice, practice. If you're following along with the video, make use of the pause button. See a problem that you like? Pause it. Try it out yourself first. And then if you want, we can compare answers, no problem. The more that you do, the better you're going to become. And the better you become, the more in the future you'll be able to achieve. And we want you to achieve amazing things. So keep at it. Well, let's begin. Our first problem. Find, and here we could say the integral, which is really the antiderivative of this expression. 27x cubed plus the square root of x cubed plus 2x to the 6th all over x to the 4th dx. Now, generally speaking, there's about 8 or 10, depending upon how you count, things that you should know the antiderivative of by heart. Almost always, we're not going to start with one of those. But the goal is to say, okay, can I break things up in a nice way? So we're thinking about things like algebra or trig, things that allow us to rewrite it. So it's like, oh yeah, we can get to something which is reasonable to work with. Now here, we say, oh, well look, you see pluses upstairs. Pluses upstairs are good. Pluses downstairs are bad. See, look, it's like your thumb tells you, upstairs, great, we love that. Downstairs, not so good, we don't want that. So what's good about pluses upstairs? What we can do is separate. So say, hey, this is the same as the integral 27x cubed over x to the 4th plus square root of x cubed over x to the 4th plus 2x to the 6th over x to the 4th and dx. All right, great. Well, now what? Well, now we know that finding antiderivatives, or if you like, integration, is linear, which means I can really think of it as 3 problems. Now, oftentimes we don't write them as 3 individual problems. We just go through and do the work. But today, let's do it, just to sort of emphasize in the back of our head, what do we see? And the other thing we can say is, oh, let's simplify. For example, x cubed over x to the 4th, well, that's really like 1 over x. And then square root of x cubed over x to the 4th. Well, the square root of x cubed is also known as x to the 3/2 power. So I have a 3/2 upstairs, a 4 downstairs, and here talking about the power. So we subtract. So if you take 3/2, or 1.5, and subtract 4, you'll get x to the minus, and we can write it as 2.5, or we could write it as minus 5/2. Either way is fine. Doesn't really matter. And dx. And plus integral here, x to the 6th, x to the 4th, that's 2x to the power 2, 6 minus 4, dx. Okay, all right, great. Well, okay, now a couple of things to know. If you wanted to, I do tend to like fractions, so let's just say this is as x to the minus 5/2. We like to write things as x to a power. And when we started, we said, oh, there's lots of x's involved, and it's good to remember the right rules. So we're like, the rule is x to the power k dx is 1 over k plus 1, x to the power k plus 1, and of course always plus c. Don't forget the plus c if we're doing these integrals here, these antiderivatives. There is one exception. Of course, you say, what about k equals minus 1? And so, for that, That's like the integral of 1 over x, and that's natural log of x plus c. So you'll notice it really is good to write things as x to a power, unless it's like x to minus 1, and then we usually leave it like 1 over x. Because we're like, oh yeah, the rule says that one's kind of special, we'll do that separately. So what do? Go through term by term. The 27 just stays as 27. Constants stay there. Antiderivative of 1 over x is log x. All right, log x. Plus, here, x to minus 5 halves. Okay, so that would be add 1. So if you add 1 to minus 5 halves, you'll get minus 3 halves. And then, remember, you have to divide in front by the new power. So 1 over minus 3 halves. What I like to say is multiply in front by the reciprocal, right? Because if you're going to divide, it's the same as multiplying by the reciprocal. And then the last piece here, well, they're 2, all right, x to the third, because you add 1 to the exponent. So if it was 2, it goes to 2 plus 1, which is 3. Divide by that new exponent, 1/3, and plus c. Now you might say, shouldn't we have had 3 plus c's? No. You only need 1. Because if you have a bunch of constants, they can all merge into one single uber constant that covers them all. All right, so we'll clean this up. 27 log of x. Here, if we flip it over, minus 2/3 x to minus 3 halves plus 2/3 x cubed plus c. And there we go. Now with practice, you'll pretty soon start to go through integrals of this pretty quickly. A lot of functions with simple antiderivatives, it's just a matter of, getting to the habit, the drill, and then you're like, okay, yeah, if I'm integrating x to the power, okay, add 1 to the exponent, multiply in front by the reciprocal, and go quick. And it's good to get to that stage because we want to be there. We want to be able to do things quickly and efficiently. All right, well, let's try another problem. Okay. So, find the integral of this function, e to the x plus 1 quantity squared dx. So, let's talk about what we can do. Now, one thing we can do is say, look, let's use our tools. And our tools here being things like algebra. I have something being squared, so we say, great, let's square it. In other words, let's do some expansion. So we'll start by expanding. And what do we get? Well, okay, this is the integral. We'll do it in a couple of steps here just so we can make sure we follow what's going along. E to the x plus 1 times e to the x plus 1. So you take the first terms, that'll be e to the x times e to the x, which is e to the 2x. You can add the exponents. Take the outer, you get e to the x, and the inner you get e to the x, so we really have 2 e to the x, and then the last plus 1. Okay, so that's what we get when we square, and then we say, wow, this is great. We can integrate 1. That's really easy. The integral of 1 is x. E to the x, beautiful. We can do that. E to the x is one of the funnest things because if you differentiate it or you integrate it, you get back to where you started. Now, e to the 2x is also not too bad. It's not very far off from e to the x. You just have to be careful about the 2. So, how do you be careful about the 2? Well, the answer is if you see if it's e to something times x, constant times x, you multiply in front by the reciprocal of the constant. It's one of our rules that we have. So if I have a function inside of a function where the inside function is really simple, a constant times x plus another constant, then I can say, okay, integrate the outside like I normally would and divide in the front by that constant. All right, integral of 2 e to the x. Well, the 2 is a constant. Integral of e to the x is e to the x. Integral of 1 is x. And don't forget at the end, plus c. And we're done. Great. Well, that wasn't so bad. And we got all this space left. Let's make an observation. Now we have what the integral is. Let's talk about what the integral isn't. Because I think it's important to recognize at the start something that doesn't work. But a lot of people are kind of like, why not? So what are we tempted to do? Well, one of the things that often happens is we look at problems like this and we think of it, oh, what if I put on my chain rule hat, right? Because I see the e to the x plus 1 inside the function being squared. Now, my chain rule hat says, oh, okay, so what I should do is I should think about taking the antiderivative of the outside function, which is like the square function, and okay, that would be the square function would be I cube it, but I leave the inside alone. Then I multiply by 1/3. And then I'm going to divide by the derivative of the inside. So this feels like sort of reverse chain rule. All right. Now, this feels kind of reasonable. It's like, oh, when I do the chain rule, that's what we should get. Is it right? And let's think about it. I'm not claiming it's right or wrong. One thing you can check is if you cube e to the x plus 1 and divide by e to the x and divide by 1/3, you're not going to get that. So these are not the same. But we should try to see why this fails, because I think if we see why it fails, then we'll start to understand things a little bit better. Now, one of the great things about antiderivatives is there is a built-in check your answer mechanism. Namely, if you have the antiderivative, take the derivative of it, and what should you do? You should get back to where you started with. So, think about taking the derivative of this function. What rule would you use? Well, one way you can think of it, you can think of it as you have a 1/3 e to the x plus 1 quantity cubed e to the minus x. So I'm going to use a product rule. Okay, so if we take the derivative there, all right, what happens? And what do we see? Well, okay, take the derivative of the first. Chain rule, okay, so we'll have 1/3 times 3, because the 3 will come down, times e to the x plus 1 quantity squared, times the derivative of e to the x plus 1, which is e to the x, and then there's an e to the minus x. Now, look at all these beautiful things that happen. We're like, wow, this is cool, because the 3's cancel, the e to the x and the e to the minus x cancel, and we're left with e to the x plus 1 quantity squared. And like, wow, hey, Steve, that's exactly what we wanted, right? Yes, but what haven't we done yet? We haven't finished taking the derivative. I have to remember to take the derivative of the second part as well. So there's plus a 1/3 e to the x plus 1 cubed times the derivative of e to the minus x, which is minus e to the minus x. And so here's why this idea of like, oh, I take the integral of the outside function divided by the derivative of the inside function, it feels like it should work because, yeah, part of it works. And you do get the right function, but then there's this extra stuff that comes in which doesn't match, and it shows up. So that's why this idea fails. It doesn't work. Okay, so be careful. That's not true. Now, when would it work? Well, it would work perfectly fine if the derivative of the second piece was 0, so that there was no second piece. Well, the derivative of the second piece would be 0 if it was a constant. That's why it works here when you take the integral of e to the 2x. See, when we divide by 2, because it's a constant, it's all fine. When it's anything more complicated, we need a better method. We will talk about better methods, But for right now, this is just our way of saying, don't try to do chain rule yet. We haven't gotten there, but we will. Chain rule is such an important rule for taking derivatives. There has to be something for antiderivatives, and we will get to it. We will get to it. I promise you. I promise you. Stay tuned. It's going to be exciting when we do it. It's just going to be a happy day. All right. Next problem. Find the integral of secant theta plus tangent theta quantity squared. All right. Well, great. Trig. We love trig. So what do? We say to ourselves, all right, well, let's start our process. We have a square, so the first reasonable thing to do is expand. So when we square this, we say, all right, that's not so bad. It would be, if I'm thinking this as a plus b quantity squared, it would be a squared secant squared, then 2ab, so 2 secant tangent, and then b squared, tangent squared. All right, d theta. Now, we have 3 pieces here. And let's go through and talk about them. So, remember, when we have plus, we can treat each one separately. So, secant squared, are we happy with secant squared? Yes, we are happy with secant squared because secant squared shows up as the derivative of something. In other words, it's on our list of things that we can take the antiderivative very easily. So we're happy, right? Yeah, okay. Secant tangent, don't worry about the 2. 2's our constant. Don't worry about the constants. Secant tangent, are we happy with secant tangent? In other words, do we recognize secant tangent as the derivative of something? Yes, it made our list. So secant tangent, wonderful thing. Woohoo! Wow, 2 for 2. And now we get to tangent squared, and we're like, do we recognize tangent squared as the derivative of something? And we're like, no, it's not on our list. And so this is, we're not happy yet. Now we're not sad because we have trig. And when we have trig, that means we have identities, things that we can use to help us rewrite the expression. So we start thinking, okay, what do we want to do? We want to rewrite tangent squared using some trig identities. And then what we think about is, how do we rewrite tangent squared? Now, in particular, we kind of have some goals. What are things that we can take antiderivatives of? Well, things related to tangent are secants and tangents. And we can do secant squared, and we can do secant tangent. So what we'd like to do is find a way to rewrite tangent squared involving secant squared and or secant times tangent. So now we start thinking through our trig identities. Now, the good news is we don't have to think too long. One of our basic trig identities, one you probably know really quickly, sine squared plus cosine squared equals 1, right? Well, start with that trig identity, divide everything by cosine squared, and sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. And so what it tells us is really a tangent squared behaves very much like a secant squared. So we can swap them for each other, except there's just this little plus 1 you got to keep track of. So in particular, we say, we can say that tangent squared is secant squared minus 1. And so if we replace it with that trig identity, and then what happens is we become happy. Woohoo! Because now we can integrate that part. So we did algebra to expand, looked at our pieces and said, hey, this piece on the end, we want to clean it up so that we have something to work with. So this becomes integral. Well, there's a secant squared and another secant squared. So 2 secant squared, and there's 2 secant tangent, and then there's the minus 1. And now, each one of these pieces is something we're happy to work with. Integral of secant squared is tangent. integral of secant times tangent is secant, and integral of 1 is theta. Now, remember what integral you're integrating with respect to. You might have said it's x, right? Well, that's if you're integrating with respect to x, but here we're integrating with respect to theta, so it's theta. And there's our answer, right? Right? Right, there's something we're missing. Okay, all right. Plus c. Remember, these are indefinite integrals, or if you like, antiderivatives, which means you need the plus c. If you don't have it, it's not right. All right, so there we go. Good. So, trig identities. They're useful. Make sure you use them. All right, our next problem. So, two students are trying to figure out the following antiderivative. So 2 times x plus 1 over 1 minus x cubed dx. Oh, all right. Jesse works on it and gets an answer. 1 plus x squared over 1 minus x quantity squared plus c. All right, well, that's great. I wonder how Jesse did that. I don't know. Now, Tracy, on the other hand, comes up with an answer of 2x over 1 minus x quantity squared plus c. All right, great. Now, I see that I forgot to write down what's the question, so let me put that in. Who's right? Because what's going on? Now, you can imagine, I know it's hard to imagine, that people would make mistakes doing calculus. Yeah, it can happen. You can not be paying attention, and you come up with the wrong answer. So here we have two different answers. Okay, so who got it right? In other words, who do we want to be part of our study group? That's a good question. It's a great question. Well, how can we think about it? Now, we don't know the process that they used to come up with their answers, so we can't really say, I know, we'll just replicate the process and check their work. All we know is their final answer. But that's actually great, because there's a way to test antiderivatives, whether they're right or wrong. What we do is we say, all right, let's take the answer, take the derivative, and then we'll see what we get. Okay, well, so let's just start with something. All right, let's start with Jesse. All right, well, what do we get? Well, we're going to take the derivative with respect to x of 1 plus x squared over 1 minus x quantity squared. All right, that feels very quotient rule. So we're going to take the bottom times the root of the top minus the top times the root of the bottom. So let's be careful here. It'll be 2 times 1 minus x times minus 1. All of that over the bottom term squared. And if 1 minus x squared squared is 1 minus x to the fourth. Now we can do a little bit of simplifying. We see, everything has a 1 minus x, so I'm going to take out a single 1 minus x off of every term. Well, that's good. We're getting a 1 minus x cubed downstairs. What are we getting upstairs? Well, let's see. If we multiply this out, we're going to get 2x minus 2x squared, right? 2x minus 2x squared. And here, there's a minus 1 and a minus. So let's go ahead and put those together. Make that a plus. And then we're going to have a 2. So there's a plus 2. And then here, plus 2x squared. Divide by 1 minus x cubed. Great. And this is good. The 2x squareds cancel. And we say, wow, look, both terms have a factor of 2. So if we pull out the 2, then we get 2 times x plus 1 upstairs, 1 minus x cubed downstairs, which is that function. That means because we took the derivative of this and got the function, this is the antiderivative. So we start thinking to ourselves, we wish that we had Jesse's answer. Do. We wish that we had Jesse's answer. Do. All right. Jesse got it right. Yes. Okay, so I guess, does that mean Tracy got it wrong? Well, I wonder what happened to Tracy. Let's try it. Let's see. Maybe if we take the derivative, it'll probably show us kind of where Tracy probably made some mistake, right? Okay, so now we'll take that derivative. So the derivative of 2x over 1 minus x squared. All right, I'm not going to worry about the plus c, because when we take the derivative, plus c goes away. All right, so similar process. We're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom. All right, great. All over the bottom squared. And now we're like, ooh, cool. Similar thing as before. We can cancel off a single 1 minus x. It's common to everything. All right, that's great news for us. All right, now what? Well, let's multiply this out. So what do we have here? Well, we're going to have a 2 minus 2x, because that 2 minus 2x. And here, a minus makes a plus. 2x times 2 is plus 4x over 1 minus x cubed. Okay, now 4x and minus 2x becomes 2x. All right, so that's really 2x plus 2 over 1 minus x cubed, because I can just add those together. Oh, we could factor out a 2, so we get x plus 1 over 1 minus x cubed. Aha! That means Tracy got it right. What? So the answer to the question of who's right is both people are right. Wow! So both Jesse and Tracy got it right. And now we have to sort of say, what happened? How is it possible that two different answers are both right? What's going on here? Hold on. Now remember, what did we say? We know that antiderivatives are not unique. They're unique up to a plus c. Well, let's look at these two answers. Maybe they're more alike than they look. So, what can we do? Well, let's think about this as our function. Let's call this f of x, and let's call this g of x. And I'm not going to worry about the plus c. I'm just really saying f of x is this part, and g of x is that part. So what we'll do is do something very simple. We'll do this expression. Let's take f of x, subtract g of x. And let's see what happens. Now, if we do it, we're going to get 1 plus x squared over 1 minus x quantity squared, subtract 2x over 1 minus x quantity squared. Well, that's 1 minus 2x plus x squared over 1 minus x squared. What's another way to say 1 minus 2x plus x squared? Another way to say that is 1 minus x squared, and then there's 1 minus x squared, which means it's 1. So it turns out that these two answers, which don't look quite the same, are not that far off. In particular, another way to say this is that f of x is g of x plus 1. So that they are off by a constant. So it is possible to get answers that look slightly different. They won't look wildly different, but they could look slightly different because they're sort of a constant that they're off by. And that's okay. Just keep that in mind. And of course, the other thing to keep in mind is it's easy to check your work, right? Because it's like, oh, take the derivative and see if I got the right function. If we didn't, uh-oh. All right. Well, that's interesting. Antiderivatives are kind of fun. Lots of fun things can happen. Well, let's do another problem. Acceleration of a particle at time t is given by some expression. It's 6 times t minus sine of t. If the location of the particle at time 0 is 7, and the location of the particle at time 1 is 12, then find the location of the position function, right? Where is it at any given time? All right, great. So we have to start thinking. We start thinking about, okay, what are we looking for? Well, we're after this position function. Okay, so that's what we know we want to find. We want to find position. What do we have? Where are we starting? Well, we have something about acceleration. So the first thing we should think about is how can we connect these two ideas together? How can we connect position and acceleration together? Well, we know a couple of things. So, for instance, if we took one derivative of position, that gave us velocity. And if we took the derivative of velocity, that gave us acceleration. So what we have is, if we have acceleration, we really have the information about the position after it's gone through 2 rounds of derivatives. So I say, aha, by taking 2 derivatives, I know what the function would be at that stage. So we want to go back actually 2 steps. Take one antiderivative. So if we start with acceleration, take one antiderivative, we'd be at velocity. Start with velocity, take an antiderivative, we'd be at position. So we say, great, we have a plan. So let's work through our plan. So our acceleration, we'll write it down for reference here, 6t minus sine of t. So velocity, well, that's the integral of acceleration. All right, so we can integrate. So we're going to integrate our function 6t minus sine of t. The integral of 6 times t, well, 6 is a constant. Integral of t, I'm thinking of this as t to the 1. Right? We can even write down t to the 1 power. So you add 1 to the exponent, t squared, divide by 2, or multiply by the reciprocal, multiply by a half. Integral of sine, that's on our list. Integral of sine, be careful, negative cosine, right? Because it's that weird thing of derivative versus antiderivative. So what we'll have is minus cosine t, and then when we take an antiderivative, there's some unknown constant. So there's a plus c. All right, well, clean that up a little bit. So we have 3t squared plus cosine t plus c. All right, now we're ready to do another round. Say, look, now we have velocity, position, that's the integral of velocity. All right, so you're going to integrate 3t squared plus cosine t plus c dt. And I might say, can we integrate plus c? And the answer is yes, because it's true that we don't know what c is. We're going to talk about that in a moment. But even though we don't know what c is, we do know what it behaves like. It's a constant. And so I can treat it like, okay, it's just a number. Think of it as you would any other number. So if it was 5, it's like, okay, I know how to integrate 5. So yeah, great. So now you know how to integrate c. Same ideas come into play. So term by term, there's a 3. Integral of t squared, add 1. That's the t cubed. Multiply by the reciprocal, 1/3. Integral of cosine, right? Be careful. Cosine is tricky, but it's at least on our list of things we can integrate. So that would be sine, positive sine. Integral of c, well, will be c times t. Anything else? Now, a constant, right? So you might say, but wait, we already have a constant. But wait, that constant came from somewhere else. There's going to be another constant. The rule is every time we take an antiderivative, there's going to be a new constant introduced. Since we took two antiderivatives, there's going to be two constants for us to figure out. Wow, cool, two things to figure out. So we really are not done because we don't have the function yet. What we have is the function up to figuring out what's this value for C and D are. So, since we have to take two antiderivatives, that means we need to solve for two constants. So we need two pieces of information. So what's our information that we have? Okay, so the first piece, location of the particle at time 0 is 7. So this is a very long way to say location of the particle at time 0 is S of 0, right? Because S is location, and when we plug in 0, is another way of saying equals 7. So that's one piece of information. The second piece, location of the particle at time 1, okay, that's S of 1, is 12, equals 12. That's our second piece. So now we have two pieces of information, and we can use them to figure out our constants. So let's see what happens. We start by plugging in 0. 0 is such a wonderful number. I strongly encourage you, if 0 is involved, use 0 often and early, right? The more we can use 0, the better, because 0 has so many things which simplify nicely. In our case, we say, look, 7 is S of 0. Okay, well, plug in 0. 0 cubed, sine of 0, C times 0. All of those are 0. Even though we don't know what C is, doesn't matter, because if you multiply a constant by 0, you get 0. So you get 0 plus 0 plus 0 plus D. And now we're like, wow, well, that's great. That's simply D. So we're like, woohoo! We know one of our constants. One to go. All right. So for our other one, well, we'll do something similar. Now with at time 1. So 12, that's our position at time 1. So, all right, plug in 1. We're going to get 1 cubed, which is 1, plus sine of 1, also known as sine of 1. Yes, it doesn't simplify. Oh, darn it. Plus C times 1. So that's plus C. Plus D. Well, we already know D, so let's go ahead and put that in. So plus 7. And now we say, okay, really 1 and 7 is 8. Move that across. And move the sine 1 across. And we say, hey, that's the same as saying C. 12 minus 8 is 4. And subtract sine of 1. And now we are like, great. So there's our value for C. Now we know everything, because we had our function up to what C and D are, but now using our information, and these are also called initial values. So using those initial values, we can solve, and we come to our conclusion that our position function at any given time is t cubed plus sine of t plus this crazy constant, 4 minus sine 1 times t, and plus 7. And that will tell us where we are at any given time. And we're done. Yeah. All right, so this is an example of an initial value problem. Well, I think we have time for one more problem, and let's do something kind of similar to the last one. Another initial value problem. So, given f double prime of x is 6x plus 2, the tangent line to y equals f of x at x equals 2 passes through the origin, and the tangent line to y equals f of x at x equals 1 is horizontal. Determine f of x. See, what do we have? We have the second derivative and some information. In fact, two pieces of information. right? Because we're told our tangent line at 2 goes through the origin. Our tangent line at 1 is horizontal. So that's fantastic. Why? Because to go from the second derivative to the second derivative to the original function, we actually have to take 2 steps. If we start with f double prime, one antiderivative gives us to f prime. A second antiderivative gets us to f. Every time we take an antiderivative, we're going to get a constant. So, because there's 2 steps, 2 constants, which means we need 2 pieces of information. And they gave us 2. So hopefully, we should be in good shape. So, let's start by saying, all right, we know f double prime of x, 6x plus 2. Let's talk about our various pieces. F prime of x, okay, so that would be the integral of 6x plus 2. In other words, we integrate the second derivative, and we say, all right, we can do that. Integral of 6x, well, okay, the integral of x is 1/2 x squared times 6 would be 3x squared. Integral of 2 is 2x and plus c. F of x, all right, that's going to be the integral of f prime. So the integral of 3x squared plus 2x plus c dx. Okay, well, the integral of 3x squared, hopefully we can get to the point where we're comfortable doing this in our head, be 3 times 1/3 x cubed, which will simplify to x cubed. Integral of 2x, well, that's 2 times 1/2 x squared, which becomes x squared, plus c would be plus c times x, and then we took an antiderivative, so there's another constant, so plus d. And notice we're using different symbols for our constants because they're different constants. And so if you have different constants, you should be using different symbols. It seems fair. And all right, great. So what's left? Well, what's left is the questions, what are C and D? Once we know what those are, we're done. So now we start thinking about our information. Okay, so what do we have? At x equals 2, our tangent line goes through the origin. And the tangent line to y equals f of x at x equals 1 is horizontal. Now, let's start with that one. That seems a little bit more interesting. What does it mean to have a horizontal tangent line? How do you know if your tangent line is horizontal? Well, a horizontal line has what property? A horizontal line has slope 0. So we say, ooh, so slope of that is 0. Now, how do you find slopes of tangent lines? You use derivatives. So this is another way of saying, hey, if we look at the derivative at time 1, that needs to equal 0. And then we say, ooh, well look, we know what our function is for the derivative, so we can say that 0, which is equal to f prime of 1, that's equal to 3 times 1 squared plus 2 times 1 plus c. Or, put another way, we say, aha, c is -5. Good. All right, great. We're good to go. Now, what's the other thing? Well, now that we have that, let's go ahead and update this, by the way. Okay, so we get x cubed plus x squared minus 5x plus d. So we have to now choose d. So our tangent line at where? At time 2 passes through the origin. Well, let's talk about our tangent line. What would that be? In general, our tangent line has the following form. So y minus f of a equals f prime of a times x minus a. So this is the tangent line at x equals a. Now you can rewrite this. Sometimes this is written as y equals f of a plus f prime of a times x minus a. That's one way to rewrite it. But for our purposes, it's probably nice to expand it. So it's f prime of a times x. So there's your slope, plus f of a minus a f prime of a. And there's your intercept. Now, we know we passed through the origin. So what we want is at x equals 2, we go through the origin. That means we need f of 2 minus 2 f prime of 2 to equal 0. Because if that's part equals 0, then that part goes away, and then you're of the form y equals constant times x. So that goes through the origin. All right, well now let's just plug stuff in. So if we plug in 2 into our function, we're going to get 8, 2 cubed, plus 4 minus 10 plus d. So 2 cubed plus 2 squared minus 5 times 2 plus d. So that's our f of 2 minus 2. And what's f prime of 2? Well, go ahead, plug it in here. F prime of 2, well, that'll be 3 times 2 squared, 12. 2 times 2, 4, plus c. Aha! We know what c is. Minus 5. And that's got to equal 0. Well, let's clean this up a little bit, right? 8 plus 4 is 12. 12 minus 10 is 2. So we'll get 2 plus d. 12 plus 4 is 16. 16 minus 5 is 11. Times minus 2 is minus 22. And that equals 0. Okay, well, move the 2 and the 22 across. You'll get d is 22 minus 2, or 20. And now we're like, great, we've got d. So we can say our function, because that's the last thing we didn't know, x cubed plus x squared minus 5x plus 22. And we're done. We found it. So this is kind of one of those fun initial value problems where it's a little bit more subtle. Like, okay, how do we translate the information into appropriate initial values? But the process is the same. We say, okay, we have some information about some derivative, in this case the second derivative, integrate the right number of times, and then use information to figure out what constants are there that came up in the process of finding the integrals. Fun stuff, fun stuff. Keep working. You're going to do great. We have high hopes for you. You're going to be awesome. And hope to see you again. Bye. Hey guys, oh, I can't believe it. A transcription error. We did get 22 showing up, but it's 22 minus 2, which is 20. So D is 20, not 22. Oh, all right, easy enough to fix. And there we go. All right, be careful. Transcription errors. They're the worst, right? Well, all right. Take care, guys. Bye.